Hello class, here are the week 14 homework solutions. Number 1, 3 times 2/5 interpreted as 2 copies of 1/5. And so in order to model 1/5, I begin by modeling 1, and then here's 1/5, here's 2/5, and then here's 3 copies of 2/5. And you wind up producing a length that we know is 6/5 right there. The next interpretation is 3 copies of 1/5 of 2. So I begin with 2, and then I do 1/5 of 2, which is what you get when you take 2 and break it into 5 equal parts. 1/5 of 2 can be shown to be the same thing as this length of, same thing as this length of 2/5 that you see right there. And then I do 3 copies of that, and that also produces the same length of 6/5. And then here's just the third one is 6 copies of 1/5. So here's 1 to begin with, here's 1/5, and then here's 6 copies of 1/5, and that's the same thing as these other lengths. And then finally, 6 divided by 5, interpreted with a partitive conceptualization. So I wanted 6 and divide it into 5 groups. So I had to draw a representation of 6. So here's 6, and notice I'm using a 1 unit length that's consistent across the board, just so we can actually compare all these lengths. Some people didn't do such things, but the way I'm doing it here helps me with the goal of showing that the final results are all equivalent in value. So here I'm treating everything in terms of lengths and showing that in the end, no matter which way of thinking I employ, I wind up with the same blue length line segment, right? They're all the identical lengths when I'm done, which is 6/5. So anyway, here's 6, and I divide that into 5 pieces. Well, here are the 5 pieces right here. One way to divide 6 into 5 pieces is to rewrite 6 as 30/5, and then divide 30/5 into 5 pieces, and that gives you 6/5. So anyway, 6/5 will be the length. That's 1/5 of 6 essentially, and it's really easy to see that if you were to copy this, if you were to copy this blue line segment right here, 2, 3, 4, 5 of them would make up this total of 6. And just for fun, here's a different representation showing 6 divided by 5 with a partitive conceptualization. 6 circles. I want to make 5 copies or 5 groups, and I did it by color coding. The first 5 go in their own group, but then the last circle needs to be split up into 5 equal parts and then shared between the 5 groups, and there are those wedges there, so that each group has 1 and 1/5 or 6/5 is the size of each group. This is doing the exact same thing, but with a partitive or with a number line approach. Right, we get 1 and 1/5 right there. 1 and 1/5 in each group. Number 2, the biggest issue with number 2 was people were comparing tree to tree. So they were saying that in 2003, tree B was 1 meter more than tree A. And in 2006, that was also true. We were trying to compare growths. So you should really be comparing tree A to tree A for the 2 years, and then tree B to tree B for the 2 years, and see what the growths are. And when you're doing additive comparisons, if you want to figure out how much more one number is than another, then you do larger number minus smaller number. So I did the 2006 height of tree A minus the 2003 height, and I get this 3 meter difference. We use the word difference because that implies this subtraction. And for tree B, we had a difference of 3 meters as well in growth. But for multiplicative, if you want to know how much larger one number is than another in terms of scale factors, then you do the larger number, which happens to be the 2006 number, divided by the 2003 number. The units of meter and meter, in effect, cancel, if you will, and you get a unitless number here. A lot of people put meter on this unit, on this 5/2, and that's not a correct unit when you're finding a scale factor. Or when you're doing multiplication, whatever unit you have times, we'll say unit 1 times unit 2 per unit 1 will give you a unit 2. This is your general structure of multiplication, but if you want to do unitless scale factors, then you just have, I'll put a number there, no unit on the scale factor, and then the unit of the multiplier and product match. Well, here we're finding unitless scale factors. We're saying, what do you have to multiply 2 meters by, scale it by, to get 5 meters? Notice this is not a meter per something. And so we're looking for a unitless number here that will scale 2 meters into 5 meters. Now, if you want, you could force a unit on there and say it's 2 meters per copy, and then put the unit of copy on here. So you would say 5 halves copies times 2 meters per copy gives me 5 meters. Some people don't like to force that unit in there or that unit down there, and they'll just say the multiplier is unitless. And that's kind of the flavor I think we're going for right here. Is we're looking for scale factors, unitless scale factors. What this is saying is that, and then we do the same thing for tree B. What this is saying is that tree B doubled in size when you get the scale factor of 2, because if you double 3 meters, you get 6 meters. It gained 3 meters in length, but it doubled in size. Don't say it gained 2 meters, because that's not true. There should be no unit on this too. Whereas tree A more than doubled in size. It was 2.5 times as large in 2006 as it was in 2003. And the language you want to say here is this times as large as. So tree A was 2.5, in 2006, tree A was 2.5 times as large as it was in 2003. Whereas for tree B in 2006 was 2 times as large as it was in 2003. You should not be putting units on these scale factors, unlike the difference where you do want to put units on the differences. So the whole purpose of this was to show that depending on how you compare these, you could answer which tree grew more in different ways. Like if you look additively, then you would say, oh, they grew the same amount. They each gained 3 meters. When you think multiplicatively, tree B only doubled, but tree A more than doubled. So you could make the argument that tree A grew more than tree B, because relative to its initial height, its final height was a greater multiple. There's some ambiguity there, and that's on purpose. Or I should say this task was made on purpose to have ambiguity so that depending on which kind of comparison you're doing of the two growths, you might be justified in defending an answer either way. Either they grew the same amount or one grew more than the other. And then this next question was, we'll assume tree B grew by the same multiplicative amount. So if tree A, the height of tree A in 2003 was multiplied by a scale factor of 2.5 to reach its new height of 5 meters. We'll assume that same scale factor. And so for tree B to experience the same multiplicative growth, it would also have to multiply by 2.5. So you would take this 3 meters right there and multiply it by 2.5 or 5 halves, and that would give you 15 halves, which is the same thing as 7.5. So if tree B had been 7.5 meters tall in 2006 instead of 6 meters, then it would have had identical growth factors, both trees. However, tree B would have gained more in height. It would have gained 4.5 meters compared to tree A's 3 meters. So again, you have ambiguity, the same multiplicative growth, but different additive growths. Number 3, I made little tables here. Boys, I counted the number of boys, the number of girls, and I did both ratios just to show you. You don't have to do both if you want to determine proportionality. The big issue I saw with number 3 was just people's language. You don't want to say ratios are proportional. You want to say ratios remain constant or ratios don't remain constant as quantities covary. So boys varied from 10 to 20. Girls varied from 15 to 25. And you do either ratio. Let's focus on the ratio of girls to boys. So you take the number of girls and divide it by the number of boys, and you get 3 halves is the ratio. Whereas for the second set of data, after they covaried, the new ratio is 5/4. So the ratios changed. Don't say the ratios are not proportional. Say the ratios changed. Therefore, the quantities are not proportional. And the quantities are the changing quantities, which is the number of boys. I was a little lazy here. I should have written this out as a sentence, but this should be read as the number of boys is not proportional to the number of girls. Because as the number of boys and number of girls change in number, their ratios don't remain constant. Whereas with this situation here where for every 3 ounces of silver, a pawn shop pays $90. So if you do 3 ounces, you pay 90. If you do double that, you're going to pay double that. If you do a third of 3, you're going to pay a third of 90. pretty much you're paying $30 for every ounce. So the ratio of dollars to ounce is always 30, and the ratios of ounces to dollars is always 1/30th. But either way you think about it, as you go from row to row, the ratios do not change. Therefore, we say that the best way is kind of just repeating what's said right here in this line. You would say the weight of the silver is proportional to the monetary value of the silver. That's really the best way to say that. Here I use units to communicate those. I said the number of ounces is proportional to the number of dollars, but it's really best said with a sentence like you see up here in the prompt. Repeat a sentence like that. In the case of the distance, in the first 2 seconds, the ball rolled 10 feet. In the next 3 seconds, so in 3 seconds elapsed, it rolled 18 feet, and the ratios are not consistent. Let's do the distance to time ratio. You get 5 and 6. So for the first 2 seconds, it was rolling 5 feet per second, and in the next 3 seconds, it sped up and was rolling 6 feet per second. But they changed, not proportional. And then the other instructions were to revise numbers. And so what I'm doing here in red is saying, instead of these numbers, 20 and 25, here are some examples of some numbers that would have maintained proportionality, or that would have suggested a proportional relationship, would have maintained the ratios. And here, so I'm going to keep row 1, but I'm saying a new row 2. So instead of 3 and 18, any of these would have been acceptable for a new row 2, so that the ratios are preserved, so that the quantities are proportional to each other. Number 4, let's see, 4 cups of liquid, that's a volume, so I'm going to call that V. Weighs 3 pounds, that's a weight, so I'll call that W. And then I simply do, I just divide these numbers in 2 different orders. If I want to do the ratio of volume to weight, then I do 4 cups divided by 3 pounds, and you get 4/3 cups per pound, which means for each pound that you have 4/3 of a cup of the liquid. And then here are the other ratios of weight to volume. In this case here, we have sugar to cocoa. This is the amount of sugar to the amount of cocoa. We just divide the number of tablespoons of sugar divided by the number of tablespoons of cocoa and simplify, so we get 9/4 teaspoon sugar per teaspoon cocoa. I'm being really lazy with these units. That S is the number of teaspoons of sugar and the C is the number of teaspoons of cocoa. And then here's an explanation of what that means. Then here's the second unit rate, just divide it the other way around. And you'll notice, of course, that the 2 unit rates that are involved in any one scenario that involves proportional quantities are reciprocals of each other, 4/3, 3/4, etc. The time to distance, I do the amount of time divided by the distance. Walked. A little mistake here. These are backwards. The first one is distance to time. This one's time to distance. Here we go. So the distance divided by the time gives you the miles per hour, and the time divided by the distance gives you the hours per mile. And so here are the 2 interpretations. Each hour he walks 4 miles, or he would take 1/4 of an hour for each mile. Number 5, okay, so tandem scaling or using unit rates. So you had to find those unit rates. You use these 2 figures to find the unit rates. I didn't really show that work over here, but I believe these are the same numbers we had involved up in an earlier problem right here. So we already found the unit rates, 4/3 cups per pound or 3/4 pounds per cup. So depending on which direction you're going, right, if you're going to start with a known number that's volume, you multiply the number of cups by 3/4 pounds per cup, and that will give you the number of pounds. So to go left to right in this table, you multiply by that unit rate. To go the other way around, right? If you know this number, if you know the weight, then you multiply by the unit rate of 4/3 cups per pound, and that will tell you how many cups you'll get. So using the green and the red are called using the unit rates. Tandem scaling is where you just recognize, okay, in order to scale 4 to 20, I'd have to scale it by 5. And you can think of 5 as a unitless scale factor. So you have 4 cups times 5 is 20 cups. So the multiplicand and product don't change units. They're the same units because your multiplier is unitless. So if you scale by 5 here, then you should scale by 5 over here. So here's 2 ways to find A. Tandem scaling means multiply 3 pounds by 5 to get 15 pounds. And using the unit rate means do 20 cups times 3/4 pounds per cup, and that will also give you 15 pounds here. So there's the two different ways to find A. Tandem scaling with a unitless multiplier, or using the unit rate with a unit on the multiplier and a rate unit on the multiplicand, and getting a product, an appropriate product. To find B is similar. To find B, I'm going to use the unit rate method right here. I'll do 2 times 4/3, or I could do the purple scaling here, right? In order to scale 3 to 2, you have to scale by a factor of 2/3. So do the same scale factor on 4, and 4 times, or 2/3 of 4 is 8/3. And then, of course, 2 pounds times 4/3 cups per pound also is 8/3 pounds. So either way you look at it, you're going to get B is 8/3 pounds. Sorry, 8/3 cups. I meant to say cups, not pounds. And then just add any row. Here's a row I added, and I just got that by tripling. There should be an X right there. I'm not sure what happened to that. By tripling B and tripling 2. Right, there's lots of ways you could have done this here. I could have also doubled 3 to get 6, and double 4 to get 8. Or you could triple 2 to get 6, and triple 8/3 to get 8. Right, lots of ways to do this. And finally, number 6. So the method that I referred to, I wasn't too picky if you use the actual method. This idea that if you do a ratio of sugar to cocoa, we got the 9/4. This is something that was in a previous problem. And you could create since the sugar and cocoa are both measured with tablespoons, you could create these empty tables, if you will, where you have 9 parts for the sugar for every 4 parts for the cocoa. So I just drew a table that has 9 parts for the sugar and 4 parts for the cocoa. And whatever you put in any one of these spaces, you just put in all of them, because they represent equal amounts. And you're totally free to put any number you want, technically, in any of these spaces to get, and then add these all up, and that's how much sugar you have, and add these up, and that's how much cocoa you should have. And that's how you can get different corresponding pairs of information for sugar and cocoa. And it turns out we could have filled in this table rather easily without even using this, so I gave full credit if you filled in this table in some sort of appropriate way. So if one recipe calls for 9/2 tablespoons sugar, 2 tablespoons cocoa, so just add those together, and we have 13/2 total tablespoons. If you want to do a third of the recipe, then you have to multiply all of these amounts by a third, essentially. So a third of 9/2 will be 3/2, and a third of 2 is 2/3. And if you add 2/3 and 3/2 together, you'll get 13/6, which is what you get if you simply do a third of 13/2. And if you want to do 4 batches of this recipe, then you just got to multiply all of these by 4, right? Multiply 2 by 4, you get 8. Multiply 9/2 by 4, you'll get 36/2, which is 18. Add those together, you 26 total tablespoons. So you could really just use tandem scaling. The number of recipes helps you see how to scale it. To go from 1 to a third, you multiply by a third. Right? To go from 1 to 4, you multiply by 4. So tandem scaling would easily fill in this table. And then plotting a bunch of different data. You should always, whenever you graph a proportional relationship, it should always be a line originating at the origin and being some sort of line that extends off into the first quadrant, passing through the data, where I forced S and C to be the horizontal and vertical axes, respectively. I could have put C here instead and S here, and your line would have been slightly different, something like that. But and here are the 2 different equations that will convert C into S and S into C. These are just the unit rates you'll see that are being used. Right? If you were to put units on all these things, then C would be measured in tablespoons of cocoa, and that's what the 4 is. Or the 9/4 is tablespoon sugar per tablespoon cocoa, and the S is measured in tablespoon sugar. So I'm leaving the units off and using S and C as variables. But here's how you convert C to S, and here's how you convert S to C, which is really just a summary of using unit rates, similar to what you see in here, how you go back and forth from one column to the next. This is kind of like what this would be. You would use these calculations to go back and forth between the 2 columns for S and C.